So just to conclude that part, there is future hurricane threats, loss of life as population increases and coastal habitation increases, sea level rises. This is obviously a great concern. Plus, we continue to remove some of the natural barriers like mangroves, coral reefs, salt marshes, wetlands, and so on, which are very good dampers of waves and hurricane energy as they come in. And there is also places where the sea level rise is being accelerated, places like Venice or New Orleans, for example, where when you remove groundwater or oil below and so on, land can actually sink, which means, relatively speaking, sea level actually rises. Venice is a very good example of how human activities can make the sea level rise problem so serious, right? Venice is very typical of a place which is living underwater almost. So those are kind of things we have to worry about. So let's look now at back to ocean. This is air-sea interaction, so it covers everything including hurricanes, because hurricanes get energy from the air-sea interaction. What are the climate patterns of the ocean? So the open ocean has climate regions which are almost parallel to latitude lines. Why? This is important to remember. We talked about Coriolis and how Coriolis effect depends on latitude. It turns out that everything on Earth is strongly constrained by Coriolis. So, moving across latitudes, you can imagine, will be difficult because Coriolis changes. So the meridional winds, or winds going towards the north, are typically never as strong as winds going east-west, zonal winds, because it's easier to go along the Coriolis than against Coriolis, right? So this is something to remember. So ocean also shows the wind patterns in them, which are mostly longitudinal, and these regions are modified by ocean currents. So this is kind of a sketch that we will see animations and other things which will show us how much more complicated they are. And one of the most important concepts of oceanography is actually in it, that I will explain in the podcast in the next chapter. So here it is showing the broad climate patterns. So the magenta color here in all the three oceans is where you have some of the warmer waters that we have talked about, and you can see the zonal asymmetry here already. On the equator here in the Pacific, the warmer waters are to the north of the equator. This is the asymmetry in the ITCZ that I mentioned before. And there's a much bigger blob of warm water on the west, where you have Australia, New Guinea, and many of the beautiful tropical West Pacific islands, Solomon Islands, Kiribati Islands, and so on and so forth. And you have the Great Barrier Reef, correct? So then you have the orangish regions, which are called still the tropics. So these are the equatorial regions, tropical regions, subtropical regions in yellow. The bluish greenish colors are temperate latitudes, and then you are getting into subpolar and polar latitudes. And you can also see the asymmetry in the southern hemisphere, which has a continuous channel in the Southern Ocean. This makes a difference because how much energy will go into the ocean depends on whether the ocean can be churned continuously like a channel, or if it will hit the land boundary when it's going from east to west or west to east. So the ocean energy can depend on how much the fetch of the winds are, the duration of the wind, and the strength of the wind, and so on. The other point to make is Indian Ocean is very different. Not unexpected. The land is coming so deep down into the tropics, and the temperature structure is very different as well, because we have the monsoonal circulation, as we will see later on. Again, we saw a little bit of it. The winds are from the southwest during this summer season in the northern hemisphere, and they become northeast during the winter season. You can again use your heat content knowledge, ocean warming slower than land, cooling slower than land, and look at the pressure. During the summer when the sun is north, land is heating faster, warmer temperature, lower pressure, ocean is warming slower, cooler temperatures, higher pressure, wind wants to go from higher pressure to lower pressure, you add Coriolis, and you end up with your southwesterly winds. You reverse the whole argument, land cooling faster in the winter than the ocean, cooler temperatures, higher pressure, winds wanting to go from land to ocean, add Coriolis, and you end up with northeasterlies. Very simple. I say it fast because you want to also have these concepts equally well established in your minds. It shouldn't take you too long to add 1 plus 1 and come up with 2. In life, if you have 1 plus 1 and come up with 2, you will always be successful. Many people come up with 5 and some people come up with 1.5, and this can be a problem. So you always need to carry multiple concepts and be able to add them all the time. So much for the philosophy. And now the currents. You can see that warm currents are going poleward on the western side. Unlike the winds which can go around and climb the mountains to the other side, ocean has boundaries except in the Southern Ocean. So as the trade winds are dragging the ocean from the east to west, the ocean currents have to decide what to do when they reach the western coast, right? Western coast of the ocean and eastern coast of the land. So this is the eastern coast of Asia and Australia, and western coast of US and South America. So warm waters go north and cold temperatures are coming south. Okay, we will see that this is one of the most important concepts of oceanography. Do the currents on the west and the east look the same? Turns out that they look very different, and that again it turns out to be related to the Coriolis effect. It's called Western Boundary Intensification. Just remember it. I'm throwing it in now. A very important concept. Okay, so these are the ocean's climate patterns. Just to wrap it up, you have equatorial region with warm temperatures, low pressure, rising air, weak winds. We call it the doldrums. The tropics have the north-south. They are north and south of the equatorial zone. They extend obviously to the Tropic of Cancer and Tropic of Capricorn. That's why we call them tropics. They have the strong trade winds. Very little precipitation because there is subsidence, clear skies, high pressure. Subtropics is the real center of the high pressure descending air. Weak winds. So it's not like Hadley cell is just going along and sinking in a little region. It's rising in a very narrow region. As it goes along, it's sinking along the way. That's why you have this kind of patterns, right? Ocean's climate zones are typically called temperate, strong westerly winds. At higher latitude, severe storms are common, especially in the winter months. That's related to this instability I talked about, trying to move air from the equator with very high angular momentum to latitudes where the angular momentum is low. Subpolar regions, which we said are getting precipitation, not the same as the tropical processes, but nonetheless there are storms bringing extensive precipitation there. You can have summer ice because of the drifts from the polar regions and so on. Icebergs and sea ice are very different. Storms can make it difficult for sea ice to build, whereas calmer winds in the summer can make surface cooling and building sea ice easier, so you can have counterintuitive seasonality of sea ice. Polar regions where the temperatures are very cold, high pressure, and in the Arctic it's all water, so you can have sea ice, but obviously the southern pole, South Pole, has land, Antarctic continent, so it has glaciers. So we will see sea ice formation and the processes, and we will see that there are ocean processes involved when sea ice is being tried to form, and this affects how thick the sea ice can get compared to glaciers on land. Okay, very interesting processes. Again, just watch these videos, make sure you are following all the concepts, because I'm just adding little concepts. Each one by itself sounds simple. The trick is that you should be able to invoke all the other processes when necessary. 1 plus 1, remember.